Impulse drive is a potentially useful application of Tetryonics, based upon the idea in T-theory that energy and its properties are fractal. In practice, we couldn't have a test particle like an electron small enough that we can use its induced motion as a result of the effect of a quanta's component fields on that electron as a way to map out that quanta's fields, because electrons themselves are comprised of quanta. The idea of an impulse drive is an attempt to answer the question, could we instead do the reverse, recreate a macroscale version of a quanta such that the motion of a mass or particle recreates the effect that a quanta's component fields should have. Instead of making a test particle small enough to interact with a quanta, we make a quanta that is big enough to interact with a macroscale test particle. This device, if possible, can be made useful by modifying such a quanta analog system so that it is open, such that as long as we continue to dump more energy into it, it can perform work against an external force like gravity. Creating a mechanical analog of such a system should also give us insight into how quanta work as a composition of fields on the quantum scale. Basically, this is an experimental pursuit of a Lagrangian description of quanta, in which we start with the description of the motion of mass and its kinetic and potential energies to derive the forces that must be acting on that mass to create those motions and changes in energy. The end goal of which is to associate those forces in the motion of the mass through real space, as well as even this change in energy throughout state space, with vector fields that are ideally equivalent or at least related to the electric and magnetic fields of which quanta should be comprised. An alternative to the Lagrangian strategy to describing physical systems is the Newtonian one, where instead of describing a system in terms of the path of its motion and changes in energy, we describe the system as being acted upon by a superposition of separate forces, and directly derive the vector fields of the forces through applying some kind of continuity or conservation law to a control mass or volume. In this video, I will relate some observations I've recently made regarding the Newtonian strategy for developing a mathematical description of tetrayonic quanta. I previously talked about how a research group's work on non-diffracting supertoroidal pulses could be relevant to modeling T-theory. These observations were a result of experimenting with recreating some of their work. A key component to deriving the non-diffracting supertoroidal pulse of Maxwell's equations is the use of something known as a Hertz vector potential. The use of Hertz vectors is a somewhat obscure strategy for making some types of electromagnetic theory problems more tractable to computation. Basically, you have an assumed form of an electric and/or magnetic vector potential as a result of an electric and/or magnetic polarization. And you can use this vector potential to derive the corresponding electric and magnetic fields. Their assumed vector potential looks like so. The general form of this function has a bunch of intriguing properties that can be related to the geometry of Tetryonics. This form of function in 3D space looks like a ball of vectors pointing in a single direction whose magnitudes decay exponentially with distance from the source of potential. If we curl this vector potential field, in the case of a solely magnetic vector potential, we get a vector field that is classically supposed to be the integral of the electric field over time, and it has a circular shape. Taking the curl of this solely magnetic potential twice results in a field that classically is supposed to be the magnetic field, and it has a toroidal shape. The toroidal field resulting from the second consecutive curl in the vector potential can be reparametrized to be conical. In a previous video, I noted that if you reparametrize curvature to occur in steps and plug this into the parametric equation for a circle, you end up with a triangle. This strategy for parametrically creating a triangle requires the use of two separate step functions which are out of phase with each other. These step functions can be constructed by performing a cumulative integral on sine and cos functions shifted up so their minimum value is 0. Transforming the toroidal vector field in this case into a conical one works in a similar way. If you take samples of the magnitude of the vector potential around a circle with one edge along the center of the source, you obviously get a Gaussian distribution. Integrating this Gaussian distribution around the circle gives you a step-like function. If you take the Gaussian pulse as being one of the inputs for curvature into the parametric equation of a circle, and the cumulative integral of the Gaussian pulse as the other input for curvature into the parametric equation for a circle, what you get is one half of a triangular shape. If you mirror this process on either side of the central axis, you get complete triangles. Since the first curl of the vector potential results in a curling circular vector field, and the second curl results in a curling toroidal field, both of these fields are divergence-free, and we technically can't use either of them as a discrete building block for modeling the electric field directly. We have to either have that its interaction with other sources of potential is divergent or convergent, Or else this curling field in the context of T-theory isn't actually the electric field at all, it's something else. Right now, it's just a mathematical tool for analytically or discretely defining tetrayonic geometries out of bent circles. There is, however, a very simple way to create a convergent curl-free field out of this potential function, and that is to transform it into a scalar potential function and simply take its gradient. And we can create a divergent vector field by taking the negative gradient of this scalar field. If we ignore the other spatial derivatives and only take higher order derivatives along the z-axis, we end up with a vector potential that alternates in polarity in a very similar fashion to the columns of a chem field. Taking successive derivatives of the exponential function simply return the exponential function but rescaled by its exponent. If in this case the exponent is less than 1, we are also recreating the continuous quantization effect that I have described in my other videos that chem fields have. For example, if you take an n equals 2 chem field, you can equivalently have it be an n equals 4 chem field as long as you rescale the magnitudes of the quantized properties appropriately. If we take the derivative of the vector potential along the z direction multiple times and then curl it twice, we get this pattern. Once again, it's like a column of a chem field if these toroidal patterns were bent to cones. Another interesting thing to note about this is that if you were to join multiple columns like this into the pattern of a chem field, you get this pattern at the bottom, such that if these were physical objects rotating, like interlocked gears, the rotation of any one causes the entire assembly to rotate in this specific alternating toroidal pattern, and that if we want to grow the pattern bigger, we need to grow it in a balanced fashion by adding one extra pair of interlocked gears on every row, creating a triangular shape. Since every row is comprised of pairs of gears, there's a successively increasing odd number of intersections of gears on every row, just like there are quanta in a chem field. Because of the properties of the exponential function, we can have the superposition of two separate opposite polarity point sources of vector potential be equivalent to the spatial derivative of one but rescaled. This is another means of connecting properties of exponential functions to practical properties of chem fields. Also, the change in sign along a spatial derivative of a bump function, like the Gaussian pulse, creates a natural connection to continuity equations, with the positive sign portion being associated with an inflow into the region occupied by the bump, and the negative sign portion an outflow from the same region. We can make these vector distributions move by including a time displacement term in the location part of the equation describing the point source with its potential. If we make the time displacement term complex valued, we can give the field's time-varying sinusoidal properties via Euler's identity and relate them now to two separate components that are out of phase with each other, which needs to be the case in order for quanta to be self-inductive like the electric and magnetic fields are with each other. You can see if we do this, the complex field corresponds to the first-order spatial derivative of the real field along the direction of propagation. Depending on where you put the complex coefficient I, you can also create sinusoidal variation throughout space. So far, this strategy for trying to define tetradic quanta in terms of familiar mathematical constructs has a lot of good things going for it, but there are some problems which I don't yet have a solution for. The main one is how to properly define superposition of separate point sources of vector potentials. For example, to make an electrostatic field, you need to join two positive quanta magnetically along their bases. It is unclear to me how to define an interaction between two like-charged vector potential sources, or unlike-charged either for that matter, such that their intrinsically associated motion is nullified and they create a static field. Arranging the sources such that they create the correct field distributions is simple. If you place a right-hand roll field source anti-parallel with left-hand roll field source, the corresponding H fields cancel and the E fields reinforce each other. You can see this by simply putting the pinky fingers of each of your hands next to each other and curling your fingers to make a thumbs up gesture. You can also imagine how placing a right-hand roll field source parallel with the left-hand roll field source would cause the corresponding E fields to cancel and the H fields to reinforce each other. This creates field distributions that make sense, but what is missing is the actual interaction that causes them to join this way. Another problem is that if we superposition the vector potentials of separate point sources directly, they will only ever completely cancel different aspects of themselves when they are perfectly overlapped, or if the point sources have the exact same location in space. This is a problem because if cancellation of different properties of point sources is required to bond separate point sources together, it is not obvious how you would tessellate separate but bonded point sources into a larger geometric structure if they all have the exact same location in space. The interaction has to be scaled somehow, possibly because it involves separate orders of derivatives of each interacting point source, or because the interaction is nonlinear. I think the interaction has to be nonlinear in some way, I just don't know how. You have to be able to have an analytic expression for the potential function of a static field versus a moving one, which means that algebraically you have to somehow be able to cancel the time displacement term of the potential function, which itself is an exponent, and you add separate exponents when multiplying a common base. This is all almost exactly like the leapfrogging toruses or vortex rings of old. Unfortunately, I did not make the leap of logic to this back then because Hertz vectors are a somewhat obscure bit of electrical engineering knowledge, and also because it is easier to make a discrete on-off value out of functions usually used for defining bandpass or stop filters, which allows you to have well-defined regions where quanta are and aren't. But these functions don't have other useful properties of the exponential function. Summary: Gaussian pulses, through properties of the exponential function, have spatial properties that can mimic aspects of tetronic geometries, and through reparametrizing curvature in terms of discrete counts of its own period around a closed loop, you can bend the corresponding spherical distributions into conical ones. As ever, what is still missing is the partial differential equations relating these spatial and temporal aspects of the Gaussian function, of which the Gaussian function is also a solution, to the different interactions between tetronic geometries. Thank you for watching.